Hello, everyone. So we have discussed different type of modeling using different types of data during this module. So what we were discussing was about the complete randomized design, and we are left with another design to discuss within this module, that is the randomized complete block design. So when it comes to randomized complete block design, which we call as RCBD, in this case, the difference between the complete randomized design and the randomized complete block design is when it comes to a CRD, you have different treatments. So we wanted to check whether there is any difference between the treatments. Now, sometimes when we are conducting CRTs, sometimes there are nuisance factors which will affect for the final output. So there are some cases where we cannot control these nuisance factors, but there are some situations we know what is the nuisance factor and the nuisance factor is somewhat controllable. In such cases, we can use this randomized complete block design in order to find out whether there is any difference between the treatments as well as whether there is any effect from these nuisance factor, that is the block. So when it comes to the advantages of conducting this RCBD, that is, it's more accurate than the CRD, because since we know there is a nuisance factor and we are going to use that as a block, and then we can analyze the block effect, so that is more accurate. And also it's relatively easy when it comes to statistical analysis. But when it comes to the disadvantages, this is not suitable when you have a large number of treatments, because in that case you have to use too much of blocks. And also the interactions between the blocks and the treatment effect, there will be an interaction, so that will increase the error. So when it comes to the general format of this RCBD, so this is how it looks like. You have several treatments and you have several blocks. Now, if you look at this diagram, let's say you have K number of treatments, so 1 to K. So you have T number of blocks. So what we do is, if you look at the first block, so that is the first row. Within the first row, we can see all the treatments, K number of treatments, right? So likewise, within each block, we have to use all the treatments. That's how we perform this RCBD. Now, in this case, if you just look at the first row, if you take the total of all the observations in the first row, that is, we get the total of the total values which are coming from the first block. So that is why we denote it as beta.1. That is the effect of the first, the total of the first block. So if you want to take the mean value, since there are K number of treatments, we have one observation for each and every cell. So that is K number of observations are there. You have to divide it by K, then you will get the mean value for the first block, which is denoted by y.1 bar. So likewise, if you get the row totals and divide it by number of treatments, you will always get the mean value for the respective block. So if you consider column wise, this in the first column, you have the first treatment, and there you have the different blocks. So you can see we have T number of blocks, that is, you have T number of observations. So if you take the total of these observations, that is the total for the first treatment. So we denote it as TO1 dot. And in this case, if you take this TO1 dot, if you divide it by T, that here you will get TO1 dot bar. So this is the general design of RCBD. So in this case, when it comes to the analysis, if you take the total of all these observations, if you denote an observation using Yij, that is where I denotes the treatments and J denotes the blocks. So since you have K number of treatments, I goes from 1 to K, and we have T number of blocks, that is J goes from 1 to T. So if you take the total of all these observations, that you will get the grand total, which is denoted by G or Y dot dot. So in this case, if you want to calculate the grand mean, you have to take the grand total divided by the number of observations. So here you have K number of treatments, T number of blocks. So altogether KT number of observations are there. So if you divide it by KT, you get the grand mean, that is Y double dot bar. So the same thing that you can find out in this case, here we get the total for each and every block, that is B dot 1. So if you take a beta dot 1, so if you take the total of these beta values, that is beta dot J, where J goes from 1 to T, and if you then divide it by KT, again you get the grand mean. Or if you are going to use the tau values, if you take tau I dot, where I goes from 1 to K, since we have K number of treatments, and if you divide it by KT, again you will get the grand mean. So in this case, if you look at the model, so if you take an observation that is denoted by Yij, this is equal to overall mean mu plus the treatment effect, that is tau I, plus the block effect beta j plus the random error. So here we have K number of treatments, so I goes from 1 to K, then T number of blocks, so J goes from 1 to T. So mu is the overall mean, tau I is the ith treatment effect, beta j is the jth block effect, and epsilon ij is the random error. So if you take this observation Yij, that is the observation due to ith treatment of jth block. So as usual, the assumptions we have here, that is, if you take the expected value of these error terms, that should be 0. So the errors are normally distributed with 0 mean and constant variance. So in this case, now since if you look at this model, so here we have 3 parameters. We have mu, we have tau I, we have beta j. So if you want to analyze, we need to find out estimators for all these 3 parameters. So we are going to use the least square method to find out the estimators. So that is, we take the error term and we have to take the squared error values and take the total of them, and then we have to minimize the total as much as possible. That's what we do in the least square method. So if you take the squared error, that is, you have the observation Yij minus mu minus tau I minus beta j squared, where I goes from 1 to K, J goes from 1 to T. Since you have 3 parameters here, mu, tau I, and beta j, what you have to do is, we can partially differentiate the equation by mu and tau I and beta j. And then also we have 2 additional constraints. Since we are interested about the treatment effect and the block effect, we can take the total, the total of beta j's and the total of tau i's, that they are equal to 0. So that is also an additional constraint. So based on these equations and these 2 constraints, we can come up with equations to find out mu and beta, mu, beta, and tau, right? So in this case, we can see, so if you take this one, now in this case, when you simplify these equations, the simplification is there, you can go through that, how you simplify. So you can see mu hat is equal to y double dot divided by kt. So that is, you have to take the grand total, divide by all the number of observations, then you can find an estimator for mu, that is mu hat. And then again, if you with these equations, we can find the equation for total sum of squares. So we know the total sum of squares is you have to take the observation minus that is the grand mean by double dot bar. Then you have to take the squared summation. So this one also, if you further simplify, yeah. So if you further simplify this total sum of squares, we can just find out equations for the residual sum of squares, the treatment sum of squares, and for the block sum of squares. So you can see if you look at the residual sum of squares, that is yij minus yi dot bar minus y dot j bar plus y double dot bar square. And likewise, if you take the treatment sum of squares, so that is t times yi dot bar minus y double dot bar squared. If you take the block sum of squares, that is y dot j bar minus y double dot bar squared times k. So in this case, we can use these equations, but I will show you we can further simplify these equations. So when you're using the equations in the examination for the calculations, you don't have to by heart these equations. You can use the simplified equations because that would be much easier. Now, when it comes to the hypothesis testing of this randomized complete block designs, so there are two hypotheses that you can test. One is whether there is a treatment effect. The other one is whether there is a block effect. So if you're interested in the treatment effect, since we denote the treatment effect by tau values, so that is H naught would be tau 1 equal to 2 equal to up to tau k equals 0. That is all the treatment effects are 0, or else H1 is at least 1 treatment effect is not equal to 0. Or you can test that using the overall mean values also, because we know the grand we can use the mean value, and then we can check for this treatment effect. We have just conducted that in CRDs as well. So we can write mu1 equal mu2 up to mu k. That is all the mean values are equal, or at least there are two mean values which are not equal, right? Or if not, you can test whether there is any difference between the block effects. So that is, block effect is denoted by beta. So that is as H naught, we can write beta 1 equal beta 2 up to beta t equals 0. That is all the block effects are equal to 0. Or as H1, you can write whether at least one block effect is there which is not equal to 0. So you can use these two hypotheses in order to test the treatment effect and the block effect in a randomized complete block design. So the interesting part is now in this case here, we have derived the equations for the total sum of squares, the residual sum of squares, the treatment sum of squares, and the block sum of square. So in this case, the important part is if you take the expected value of these treatment sum of squares, you will get that is equal to k minus 1 times sigma squared plus this term, that is t into summation tau I squared. If you take the expected value of blocks sum of squares, that is t minus 1 sigma squared plus k times summation beta j squared. And then if you take the expected value of the residual sum of squares, you can see that is k minus 1 into t minus 1 sigma squared. So what I can do is I can take this k minus 1 into t minus 1 to this side, and then we will see if you take the expected value of this, that would be equal to sigma squared. So when you take the residual sum of squares and if you divide it by k minus 1 to t minus 1, that is the degrees of freedom which is associated with residual sum of squares. So that is, you will get the residual mean square value. So that is when you take the expected value of the residual mean squares, that is equal to sigma square. So when it comes to, so you can see if the residual mean square expected value is equal to sigma square, that is, it's an unbiased estimator for sigma square. So one thing that we can see, that is residual mean square is an unbiased estimator for sigma square. And another thing, now when it comes to expected value of treatment sum of squares and the block sum of squares, under H naught, we believe all the treatments are equal and all the blocks are equal, or the block effects are equal to 0 and all the treatment effects are equal to 0. So when H naught is true, when you take the summation of tau I squared, that will be equal to 0. And when you take the summation of beta j squared, that would be equal to 0. So that is under H naught, if you take the expected value of treatment sum of squares, you have k minus 1 times sigma square. This part will be 0. And expected value of block sum of squares, that is t minus 1 times sigma square. So if you do the same thing, that is, if you take the expected value of treatment sum of squares under H naught, that is k minus 1 times sigma square. So if you divide this by k minus 1, that is expected value of treatment sum of squares divided by k minus 1. That is the associated degrees of freedom of the treatment sum of squares, because we have k number of treatments. So that is, you have the treatment mean square, that is the expected value of treatment mean square, that is equal to sigma square. Same thing we can show for the expected value of block mean square, that is also equal to sigma square. So we can see under H naught, both treatment mean square and the block mean square are unbiased estimators for sigma. So we can show with these results, when you take the residual sum of squares, that is having chi-square distribution, right? Sigma square times chi-square k minus 1 t minus 1, and treatment sum of squares also distributed like this, and the block sum of square also sigma square times chi-square t minus 1. So what we can do is, now you can just perform the ANOVA table for RCBD. So that is, we have the sources of variation, which is coming from the treatments, blocks, residuals, and finally total. Then the sum of square values, the degrees of freedom value, and the mean square value. And finally, the F ratio. Now, when it comes to the ANOVA table in RCBD, what you have to do is, when it comes to the treatment, what you have to do is, you have to take, like when you take each block, you have all the treatments. So you have to go by blocks, right? So that is, you have to take yi dot bar minus y double dot bar squared summation into t. So likewise, when it comes to block sum of square, that is y dot bar minus y double dot bar squared summation times k. So you have to remember these two equations. And when it comes to the total sum of squares, yij minus the grand mean squared summation. So to find the residual sum of squares, we can take this total sum of squares and subtract the summation of the treatment sum of squares and the block sum of squares. So when it comes to the degrees of freedom from the treatment, since we have k number of treatments, the degrees of freedom is k minus 1. And when it comes to blocks, since we have t number of blocks, the degrees of freedom is t minus 1. And when it comes to residuals, that is k minus 1 up into t minus 1. And when it comes to total, the degrees of freedom, altogether we have kt number of observations minus 1. So in this case, if you take the treatment sum of squares divided by k minus 1, the respective degrees of freedom, you get the mean square value. If you can take the block sum of square divided by t minus 1, the respective degrees of freedom, you get the block mean square. And if you get the residual sum of square divided by k minus 1 times t minus 1, that is the respective degrees of freedom, you get the residual mean square. Now here we are interested in two types of hypotheses. So one is about the treatment effect, the other one is about the block effect. So what you can do is you can take the treatment mean square, divide by the residual mean square, then with that F ratio, you can use that to test the treatment effect. So when it comes to treatment mean square, the degrees of freedom is k minus 1. Residual k minus 1 into t minus 1. So from the F table, you have to check fk minus 1 as the degrees of freedom of the numerator and k minus 1 into t minus 1 as the degrees of freedom of the denominator. And then when it comes to block, you can take the block mean square divided by the residual mean square. So again, the block mean square degrees of freedom is t minus 1. So from the, when you compare the table values from the table, you have to check the numerator's degrees of freedom as t minus 1 and the denominator's degrees of freedom as k minus 1 into t minus 1. So if we, what you can do is when it comes to, after doing all the calculations, if this, the calculated value is greater than the table values, you can reject H naught. So if you first reject this first, if you compare this first F value, this first one, that ft value, if the ft calculated ft is greater than the table ft value, then you can reject H naught. So that is, there is a treatment effects. All the treatments are not equal to 0 is H naught. If you are rejecting that, that is, there exists a treatment effect. So that is, you have to go for multiple comparisons as we discussed in previous lectures when we are conducting CRD. So when you take FB, that is the second F value, and if you compare that with the table F value, if this calculated FB value is greater than the table value, again you can reject H naught dash, that is, there is a block effect. So usually in this case, we are not going to do further analysis when there is an effect from block, because that is our nuisance factor. So there's another one now. If you are going to, when in the examination, when you want to do the calculations of this ANOVA table for RCBD, you can use these equations, or you can further simplify these sum of squared values. And then you can see when it comes to treatment sum of squares, you can use yi dot square divided by t minus y double dot square divided by kt. So when it comes to block, you can further simplify, and again y dot j square divided by k minus y double dot square divided by kt. And also you can further simplify the total sum of squares as well. So in that case, you can take yij square minus y double dot bar divided by kt. So you can use whatever the equation which is easy for you. Now let's look at this example. So in this case, there are 4 different tips are produced. So we want to check out when you use these 4 different tips for reading, there is any difference in the reading. So but there's a problem, because these machine readings, they are also depending on the available metal coupon. So this metal coupon is also a nuisance factor. So we can consider the metal coupon as a block. So you can see there are 4 different types of metal coupons. That is, we have 4 blocks, and we have 4 number of tips. That is, we have 4 treatments. So When we are going to analyze a question like this, when you're going to analyze a RCBD problem, the easiest way to do is, now the first thing is you have to identify what are the treatments and what are the blocks. So in this case, tips are your treatments and coupons are your blocks. So the first thing you can do is you can find out the total value for each treatment and the total value for each block. That would be the easiest thing to do. So in this case, if you take the first treatment, you can take the total by adding up these values. That is 9.3, 9.4, 9.6, and 10. That would be add up to 38.3. Likewise, for each treatment, you can take the total. And since you have 4 treatments, if you divide 38.3 by 4, you get the mean as 9.575. And likewise, we can get the total for each and every block as well. If you take the first block, that is your first column, that is the first coupon. If you take 9.3, 9.4, 9.2, 9.7, if you take the total, that is adding up to 37.6. Since there are 4 treatments, you can divide it by 4, that is 9.4, the mean value. So likewise, you can calculate the total for each block and treatment and the mean values as well. So in this case, we can write down 2 hypotheses. We can check whether there is a treatment effect. Also, we can check whether there is a block effect. So if there's a treatment effect, we can write to 1 equal to 2 equal to k equals 0. That is, all the treatment effects are equal to 0, whereas H1, at least one treatment effect is not equal to 0. And if we are testing for the block effect, beta 1, beta 2 up to beta t, all the block effects are equal to 0, or at least one block effect is not equal to 0. So I'm going to use the simplified equations to find out these values. So first we can find the treatment sum of squares values, that is yi dot square divided by t minus y double dot square divided by kt. So that is, when it comes to y double dot, so that is what you have to do is, y double dot means the total of all the observations. So in this case, you can find here you have the total of all the rows. If you take the total of all these 4 values, you will get the total, or else if you consider the total of all these 4 values, again you get the total. So anyway, you get the same number. So if you check, the grand total would be 154. So to this part, that is for the second term, you have to take 154 into 154 divided by kt. So that is 4 into 4. K is the number of treatments. We have 4. T is number of blocks. Again, we have 4. 4 into 4 is 16. So 154 square divided by 16 here. So that is 1482.25. And when it comes to the first term, that is yi dot bar divided by t. So t is the number of blocks, that is equal to 4. So yi dot bar square. So that is I is for the treatment. So here you have to check for the first treatment, that is the first step. So this is the value that comes for the under first treatment. These are the values which comes under first treatment. So that total is 38.3. So what you have to do is you have to take the squared value, 38.3 squared, 38.4 squared, 37.8 squared, 39.5 squared. I'm reading the total with respective to the treatments, and then take the squared values, and then you have to divide it by 4, since you have 4 number of blocks. Then you get 1482.635. Then the difference is equal to 0.385. So when it comes to the blocks, you can see when it comes to the blocks, so for the first block, if you take the total 37.6, so what you have to do is you have to square this value, 37.6 squared plus 37.7 squared, 38.9 squared, 39.8 squared, and divided by the number of treatments, that is again 4 minus this term is same as the previous one, that is 1482.25. Then the block sum of squares is 0.825. Then again we can find this value. So then you can just calculate the total sum of squares using this equation. So after calculating, that is, you have to take each and every observation, subtract the grand mean, and take the square total. So you will get 1.29 as the total. So you have 1.29 as the total, and we calculated the sum of square treatment and sum of square block. So 1.29 minus 0.385 minus 0.825, you will get the residual sum of squares, that is 0.08. And when it comes to degrees of freedom, since you have 4 number of treatments, 4 minus 1, that is 3, and 4 blocks, 4 minus 1, that is 3, and 3 into 3, the residual degrees of freedom, that is 9. So altogether 16 observations, 16 minus 1, that is 50. So you can divide these sum of square values by the degrees of freedoms to obtain the mean square values. And then again, the mean square value you can divide by the residual mean square to find the F T, that is the F ratio with respect to treatments, and then this mean square value of block you can divide by mean square residual to find the F ratio with respect to blocks, and the first one with respect to treatments. So if you just check the table F value, that is, in this case it's the same, because here the number of treatments and number of blocks are the same. So you have to check F39 from the F table. So you will see that is 3.8625. So you can see when you compare the calculated F values, they are greater than the table values. So you can reject both hypotheses. So if you are rejecting the first hypothesis, that is, there is a treatment effect. So you have to go for multiple comparisons. And if when you are rejecting the second hypothesis, that is, there is a block effect, there is this nuisance factor, so that is also important. So once you conduct this RCBD, if you can reject the first hypothesis, that is about the treatments, that is, there is a treatment effect, so you cannot stop your analysis, you have to go for multiple comparisons, as we have discussed in earlier sessions. So with that, we can conclude our module. So this is how we conduct the RCBD. So just practice this question, do all the calculations manually, and see whether you get the same results. So thank you.